Hello guys, so in this tutorial I'm going to take you through how you can run YOLOv8 right in your Python IDE. So by the end of this tutorial you will learn how to run inference on an image and also learn how to detect objects through your webcam. You will also learn how to extract important information such as the bounding box, detection confidence and class names. There is a lot to learn from this single tutorial, so stick around to the end and learn more. Alright guys, so we'll start the installation process and also look at the files we'll be using in this particular tutorial. So let's begin with the file. The first file we'll be using here is the classes.txt file, which contains some common objects in the Cocoa dataset that we'll be detecting in this tutorial. And also I'm having an image here of myself that will be running inference on to check how accurate the model will detect it. Okay, so now let's just open our terminal. I'm using PyCharm. Any ID you are using, you can just open the terminal, and now we'll install the dependencies, the libraries we'll need in this particular tutorial. So first we'll need OPCV. For me, I've installed this beforehand, so you just have to write pip install, then you write OPCV -python, then you have to click enter. It will load and install. And the second library we install is Ultralytics. So pip install, then you type Ultralytics just like this and you click enter, and it will also install successfully. So after this step, you just have to minimize your terminal, right click on your virtual environment, the name you've used for that. So I use tech-watt in this case. Then you go to new, then you go to Python file, then you name the file. So we'll name this file YOLO in IDE. We are running YOLO in IDE, so just put IDE here and then click enter. Since we are using PyCharm, the .py extension will be added to it automatically. Okay, so with this done, we'll go ahead now and import YOLO. So to import it, we just write from Ultralytics. Is it Ultralytics? Okay, we are going to import YOLO. So all caps. Then the second library we are going to import in this case is OPCV. So we'll just write import, then we import CV2, not CVzone, CV2. Okay, so these are the libraries we'll be using. We'll also be using math, so let's import math, and this is fine. So what we'll do now is to run an inference on an image. So let's first create a YOLO model. Let's store this in a variable called model, and this is equal to YOLO. Then inside here we give it the name of the model, particular model we want to use. So we'll use the nano version of the YOLO models. We have large, medium and nano. Since I'm using a computer with no GPU, we'll go with the nano so that we can get some speed. So you can try it. If you have GPU, you can try, and I'll show you. So you just have to write YOLOv8n then .pt, just like this, and it will load it for you. So let's go ahead and run this to see whether or not our model will be downloaded. Okay, so you can see the model start downloading. This will take some time, so it's at 29% and it will download the nano version. So let's give it some time and I'll be right back after the downloads. Okay, so guys, now our model has successfully been downloaded, and the next step we have to do now is to run inference on our picture. So I told you that I have a picture here before we started, so write inference on this picture to see whether or not it will be detected. And to do that, we can just write, save this in result, and this is equal to our model. Then inside here we give the path to our picture. So since this is the same directory we are working, we just have to type the name. Okay, so this is the name of it, and then we'll have to specify another parameter here, which is show, and we'll equal it to true. So after this, we have to wait so that the picture can stay on the screen. So we use CV2 for that, and we can go ahead and test this out. So let's run it real quick. Wow, so this is the result. You can see I've been detected with a bounding box class person with accuracy of 93%. So this works. So this is how simple it is to run inference on a picture, and this is the reason why everybody is loving YOLO version 8, because of simplicity. It makes everything very simple for you. So this is how you just do it, and I know it's just few lines of code. So this is how we do it. We can comment this now, and now let's see how we can detect objects from our webcam. So I will write a comment here, running inference, if I'm correct, on images. So this is how you run inference on images using only 3 lines of code. Now we have to go ahead and work with the webcam, how we can actually get our webcam feed, and we use our model to detect some objects around us. So with that, we have to just get our feed from the webcam, which we have been doing so far. So cv2.video capture, and the index of your camera, you put it here. And the next thing is to create a while loop, since we'll be taking each frame. So while true, which is the same as while 1, we are going to read from our capture object. So we just say cap.read, then we pass in nothing. So this returns our frame and other stuff we don't need. So for that, we go underscore, and the frame is the next parameter. We just take it just like this. So now we've gotten our frame. We just have to go ahead and show it. So we use tv2.imshow and provide the name of the frame and whatever we want to show. So we want to show our frame in this case. After this, we have to wait, just as we have done here. So we can borrow this line here, since I'm lazy to type, and then instead of 0, put in 1 here to get a feed from the camera. So what you can also do here is to change this number, which is 0, you can change it to 1, 2. That's if you are working with multiple cameras and you want to work with a particular one in mind. You just change them to see which particular camera correspond to which number in this case. So I'll go ahead and run this. Okay guys, so I'm here live in your webcam feed. So continue now to use the YOLO model to detect some object. So for that, we'll come down here, and what we'll do is to call our model. So we just have to borrow this same model and result line here and bring it down. So put it here right before our capture object. So in here we are just loading our model. Then down here we can just cut this and bring it after our frame and say okay. So we put in our frame here, and we said string is equal to true, and close it up. So with this, we are just giving our frame to our model to see whether it will get some objects in this model. Okay, so now speaking of objects, what are the objects that this model can detect? So by default, it can detect any object in the Cocoa dataset. These include person, bicycle, motorbikes, aeroplane, bus, train, and so on. So it's about 82 of them. So we have to be able to read in this class so that whenever we detect some object, we can get its corresponding class name. So for that, we'll just come here and read the class in. So let's create a list called class name. Class names, which is equal to an empty list. And now to read a file, we just say with open, and then the name of the file, which is classes.txt. And now we want it to be in the reading mode. We are reading it as, let's use F here. So we have to go ahead and read it into our class. So we say class names is equal to not dot. So this is equal to our f.read. Then we want each one to be on a separate line, so we use split lines just as this. So after this, what we can also do is to check how many staffs is in the class, but we'll do that later on. Okay, so that's fine. So now we are able to read everything in this list into our Python file. You can try to check this by maybe grabbing the first item in the class list. So we can print class names at index 0. So if everything works well, then it should give us person here, right? So let's run this and check. Immediately we get person, we can quit from our frame. Okay, so you can see the first thing here is person, which is at index 0, and it's the same thing here. So that means whatever we are reading is working well. So we can get rid of it now and continue. Okay, so the important stuff we need now is to get our bounding box, our detection confidence, and our class names, right? And all those stuffs are saved in this variable result here. So we just have to loop over this variable and try and get those important informations. So what we can do is that we can say for, I'm writing from, we can say for results, that's results. So we can say for our info in our results, we can now say our, let's say our boxes is equal to info. And now what we'll do is to iterate through boxes and get all our information. So we can say for our box in boxes, that's correct. For our box in boxes, let's first get our bounding box. So we say x1, y1, then x2, y2 is equal to our box dot xy xy. So with this, you'll be able to get your 4 coordinates for the bounding box for the particular object detected. So x1, y1, and you can use this to draw it around whatever you have detected, which we'll be doing. Another thing we can also get is our confidence. So we can store that in a variable called conf, which is equal to our box dot conf, just like this. And what you have to do is that these have numerous lists, so we'll always take all of them from the first index. So the first index. Let's also get the class names, so we can call them names is equal to our box dot CLS, which stands for class name, at the 0th index. Okay, so these are all we need from whatever is stored in these results. Now we need the bounding box information, which we have gotten here. We need the confidence, which is how confident is this particular class detected. If it's a person, just as we have run the inference on the picture and we've gotten 0.93% or so, we want to know how sure the model is predicting that that particular image it has detected is a person, right? So that's how we go about it. Now what we have to also do is to convert the bounding box values to integer, because in order to draw we can't use floating numbers to draw. So what we'll do is that our x1, y1, instead of writing, we can just copy again the same thing here. We'll come down here to paste them. So this is equal to integer of x1. We do the same thing for all of them. And the next thing is to also convert the confidence to an integer, because it's a floating point value. We use the math library to do that, so we can still store it in a conf variable, and this is equal to, we use math.ceil. You can either use math.ceil or math.floor, and what we want to seal is our confidence value, and we want to multiply it by 100 so that we'll get it in percentage direct. So if it's 80, we just get 80 and not 0.8. Okay, so that's it. Let's do same for our names. So we say our names is equal to integer value of our name, and that's it. Okay, so with the conversions out of the way, what we can do is to go ahead and draw a rectangle around whatever we have detected. So we can say cv2.rectangle. In here we put in our frame, then the points. So the first point will be x1 and y1. We'll give it a second point being x2 and y2. Okay, we need our color, so let's give it red. And the last thing is the thickness of the color, so let's put it 2 for now. We can change. So this is what we need to draw our rectangle around whatever we've detected. So let's run this and see. Okay, so we are getting some errors. So it said object has no attribute xy. So let's check. Okay, so the problem is that from here we should write info.boxes and not just info there. So you should put info.boxes so that you can get your information. Let's run this, and I hope it's probably going to work this time. Okay, so you can see, okay, so we have some object detected now. We are having some false detections also. So what we'll do now is to put the text of whatever we are detecting on the bounding box so that we know the class and the confidence as well. So let's go ahead and do that. I'll close this up, and for that let's import cvzone so that we can get a nice text. So we said import cvzone, and we'll just come here and say cvzone.putText. Okay, we give it our frame, and the text we want to put here, we want to put both our detection confidence and the class name. So let's first put the class name. So let's use f-string here, and the first thing we want to put is our class name, the name of the class detected. So we have it here, names, but we want to get the actual class, so we'll use our class names here. So what we'll do is that we'll just put our class names in the index of our names, right? Then apart from that, we also want to put our detection confidence. So we'll just put conf here, and that's that. Let's add percentage sign to it, so I'll put percentage sign here. Okay, so that's it. The second thing is the position at where we want to put it. So for the position, we can place it on top of our rectangle. So on top will be x1 and y1, right? Let's try x1 and y1. Let's subtract some values, or let's add s1, let's add 8 to it, and subtract 12 from, so that it will be on top exactly. We can also specify scale, the scale of the text, so we can make it 1.5. And then the last thing is the thickness. We can make it 2 in this case. So let's run this up and check. Okay, so you can see person is detected. You can see we have some false detections too. Person. Okay, why? There is a mistake somewhere. So let's figure it out, because everything is detecting now as person. So let's close this up and see. Oh, okay, class name in the index of 0, no, in the index of our names. So this is the mistake. It should be in the index of our names we've read here and not 0, because if we put 0 automatically we are saying you should detect person, because it's the first thing there. So let's give this a try again. Okay, so you can see it's detecting the potted plant, detecting person, detecting the robot tie as a clock. So but the confidence is somehow down 48, 58, so we can get rid of it. Detecting another potted plant here, which is right. So what we'll do now is, in order to get rid of this false detection, we can detect based on the confidence or the percentage. So I'll just close this up and we can come somewhere here. So for that, I think we can cut it and put it here so that we can use it at the top. So let me put it somewhere here. Can give space for separation. And what we'll do is that we can use simple if here, that if our conf is greater than, let's say, 70, that's where we are going to detect and consider it as a true detection. So we'll run this now. You'll see when it runs successfully, all the false detections will be gone because their confidence is not high at all. Okay, so you can see now it's only detecting the potted plants, the 2 potted plants, and myself as a person. What I'll do is that I have a TV remote here, so I'll raise it to see whether or not it will detect. Okay, so that's fine. We are getting TV remote, or we are getting remote. So it's slow because we are not using GPU, we are just running this on CPU, and the accuracy too, this can perform better because we are using the nano version of the model. So if we should use large or the medium version, you can see we'll get higher accuracy, but because we have no GPU, it will be very slow. Let's try with a mobile phone. Wow, so it got it right, a cell phone. So this is working nice. You can see it's just detecting, and this is very easy It's the easiest among all the YOLO versions released so far. Just run this in your IDE with few lines of code. You are able to extract all the stuffs. So this is working nice, guys. So if you want to change maybe to the large version, just change the N here, which stands for nano, then you put an L here for large, and to download you put N for medium, and so on. So the code for this whole tutorial will be on my GitHub repo. You can just download it and use it yourself. You can test it out and see how it performs. Also, let me have your thoughts in the comment section, what you'll be using this for, how you've seen it so far as compared to other YOLO versions. So thanks for hooking around. We'll bring this tutorial to an end here. Thank you so much for watching. I'll meet you in the next tutorial.